All right, so I wanted to go through some of the specifics regarding the solution to homework 4 in bridge engineering this semester. What I've done is I've gone through and built a pretty comprehensive Excel template that will probably help guide you all towards your design project. One of the things I'll point out is while I'm not going to send out the Excel sheet, I want you all to build this one yourself, I am going to go through some of the specifics. The nice thing about YouTube is you can pause and replay to your heart's content. So I may be going through a lot of the formulas and calculations somewhat quickly, but the nice thing is you can always stop and review if necessary. Another point I'll make is that while this video is primarily intended for assistance with a particular homework assignment and a particular project within this class, this information will work very well for just anybody in general who wants to go through this process for a simply supported bridge. This is, I think, will be a pretty nice overview of at least the beginning stages of a bridge design. There's still a fair amount of work to be done to complete the design. We're not going to be talking about shear assessment in this video. We're not going to be talking about fatigue or fatigue stud spacing or shear stud spacing or constructability. That's going to come in the next couple weeks remaining in the semester. But this, I think, should provide a nice little overview of everything so far. I'll probably be posting another video in the not too distant future to discuss live load deflection. It's a fairly basic check. It's pretty straightforward, and it doesn't require a fair amount of computations. So we'll discuss that later. Right now, what I want to discuss is strength 1 and service 2 as they relate to bending. And I want to do this from start to finish. So the Excel sheet that I'm going to bring up is going to seem fairly large and fairly comprehensive because it is. The idea is that with minimal input, you can do an incredible amount of calculations in Excel and do them pretty expeditiously. So with that, let's go ahead and get started. I'm going to pull up my Excel sheet. Now I'm going to do my best to hone in on the formulas that I think are the most valid and are the most worthwhile to point out. A couple things about the formatting. One of the things that you'll notice is that there's a series of colors used for the cells. For instance, if you look at these cells here and let's say here and here and what have you, they come out, I've colored them orange. Those are all of the inputs that are required for the analysis, things like the girder spacing, the haunch, the yield stress, and what have you. Anything that's orange is an input. Everything else is calculated. So for instance, the modular ratio of 8, that's not an input, that's actually a calculated value based on other inputs. Now the goal is really to hone in on these 6 green cells right here, which are the dimensions of the girder: the width and thickness of the top flange, the width and thickness of the bottom flange, and the depth and thickness of the web. And that's really the whole point behind what this series of calculations is intended to refine. Now, a couple points before I begin. So number one, I have designed this particular set of spreadsheets and calculations for a homogeneous girder. So in all instances, the hybrid girder factor is going to be taken to equal 1, and we're going to be treating the girder with a single grade of steel with a yield stress of 50 KSI. If you have a hybrid girder, you'll probably have to tweak some things here and there throughout the sheet, but in the end, I think it would be pretty straightforward. And the last thing I'll point out is I've laid this series of calculations out the way that I like to do it. But the nice thing about Excel is you can arrange this in any fashion that you would like. Now, if I zoom out a little bit from the sheet, you can kind of see why I've laid it out the way that I have. If you notice, if I hit File and let's say Print, and I print to say an Adobe PDF, each sheet will be restricted to a single 8.5 by 11 PDF. And the idea is that if you would have to insert these, let's say in a calculation notebook for a project, that everything's formatted to fit within that particular set of dimensions. So, but that's how I formatted it. If you formatted it your way, you can do whatever you would like. And one point I will mention that the design project for this course is focused on an interior girder. If we were focusing on an exterior girder, we would obviously need to use different lively distribution factors. And depending upon the layout, we might want to even assess dead load distribution. Maybe we want to lump a little more load on the exterior girders due to barrier weights and things like that. But all in all, I think this is pretty straightforward. So to get started, I've got a series of sheets here on the bottom. And you notice I'm starting with section properties. I'm going to take each of these sheets one at a time. So let's start off with section properties. Now, if you've paid attention to this series of videos or been in the class, this layout should be pretty familiar regarding some of the stuff we've discussed this semester. Now, because I'm dealing with a simply supported bridge in positive bending, I don't need to compute section properties for the steel plus longitudinal reinforcement. So you'll notice all these are gone. And to be perfectly honest, I could probably delete these rows here and these rows here, since they are related to an exterior girder. Since I'm dealing only with an interior girder in this project, I could probably delete them, but since we've built these sheets previously, I just use them, essentially copy and paste. Now, one point that I'll bring up, one difference between what is going on in this sheet and what we've seen previously is this box right here. Now, this box is the assessment of the cross-section proportion limits according to Article 610.2. So if you open that up in the spec, and we've talked about that before in class, there are a series of limits that the girder needs to meet. For instance, the web slenderness must be less than or equal to 150. So for instance, I'm computing the web slenderness right here under the value column, and you'll notice D14 over C14, that's just the web depth divided by the web thickness. My limit in that, if I'm dealing with a girder that is not longitudinally stiffened, is 150. So I have a pretty simple if-then statement right here. If that limit is less than or equal to 150, or I could just say less than or equal to that, if I wanted to be a little more pragmatic about it or a little more efficient about it, I could say if that value is less than or equal to 150, then that check is okay. In other words, that's good. If it's not, then I report NG, no good. So if I go ahead and hit enter, you'll notice since 96 is less than or equal to 150, that is in fact okay. If I were to go over to the section dimensions and say, you know what, let's make the flange width, I don't know, 34 inches, well, the web, sorry, I'm looking at the web. If I would make the web depth, I don't know, something like, instead of 42, make it 142, then obviously that limit would be no good because the web is quite slender at that dimension. So I wanted to put this set of calculations right here next to the input for the girders, so that if I start tweaking dimensions for the flanges and the webs and what have you, if I start tweaking those values, then I can automatically see whether or not my girder makes sense. And I've got flange slenderness limits, the idea that the width divided by 2 times the thickness of the flange must be less than or equal to 12. So I've got those values here. Now, for the ratio of the web depth and the flange width, what I've done is I've divided those values. The limit is 6, and the long and short of it is if that value is less than or equal to 6, then the ratio is good. I did that in order to keep the format of the arrangement pretty straightforward. I wanted to have essentially a slenderness value and a slenderness limit. Now, the only one that I think takes a little bit of attention is these limits right here. Instead of worrying about whether this value is less than or equal to the particular limit, here we want the value to be greater than or equal to 1.1. So you'll notice all of these if-then statements, they're less than or equal, less than or equal, less than or equal, but as soon as we check that flange thickness to web thickness ratio, we're looking at greater than, because we want a pretty beefy flange in relation to our web thickness. Now the last one is the T-section check, and basically we talked about this check in class, but the idea is for the T-section check is that you want the flanges to be proportioned so that you don't have one flange that's monstrously larger than the other. In other words, you want to be dealing with a true I shape, or at least a close enough I shape. And the idea is that the moment of inertia of each flange about their individual strong axes, the ratio of those must be less than 10. So the way that I've done that in Excel is I've basically said the maximum moment of inertia of each flange divided by the minimum moment of inertia of each flange must be less than or equal to 10. And you notice this girder that I have input is the girder from our design example that we've been looking at all semester. Now, for the example we're going to discuss with this sheet, this girder is going to be grossly over-designed because the dimensions and the parameters that I've input is for a 40-foot simply supported bridge. So this beam is way overkill. But the idea is that once you have the sheet set up, you can tweak those dimensions to your heart's content in order to achieve an optimum solution. Okay, so here are the section properties as well as cross-section proportion limits. And again, I don't want to belabor this too much because a lot of this is derivative of stuff that we've done before in class. So it doesn't really require too much strenuous attention. Now, next comes the dead loads. Now, for this particular example, I'm assuming that I have a bridge that is simply supported, and you'll notice the span length is 40 foot long, and I have that input on the previous sheet down here below. Because this is a simply supported beam with a uniformly distributed load, this is one of the most fundamental analyses in all of structural analysis. So you can either derive or just look up the formulas for shear and moment. So for instance, moment at some distance x from, let's say, the left support is Wx over 2 times L minus x. And for the shear, it's W times L over 2 minus x. So because this is the situation I'm dealing with, I don't need to really use a fancy analytical engine to calculate these moments and shears. I can just go off of basic structural analysis. The only thing I need are the actual loads. I need the distributed load according to DC1, the distributed load according to DC2, and the distributed load according to DW. Now what I've done is instead of calculating this on the side, using a sheet of scratch paper and calculating it out, the idea is, well, I have all of the inputs in the sheet, just use the sheet to compute all of the appropriate values. So, for instance, the girder, I've already calculated the area of the girder. It's in cell D36 on the previous sheet. So you go to cell D36 on the previous sheet, and that's right here. That's the area of the girder that's been computed. So if I go to right here, I take that area, I divide it by 144 to get it into square feet, multiply it by 0.49 to the unit weight of structural steel to get kips per foot. And there's really no reason to do that off the side. The spreadsheet does that for me. So each one of these particular loads, the girder, the miscellaneous details, which was assumed to be 5% of the girder weight, the SIP forms, the slab, the haunch, the taper, all of those have been computed based on the inputs on the previous page and just drug over here. Sum everything up and you get DC1 to be about 1.29 kips per foot. So there's really no reason to do that on the side. You can just have the sheet do it for you. For the barrier, we do have to input a particular weight. For design example for the one we've been doing in class, I believe we had a barrier that was 520 pounds per foot. But I believe for your project, it's 500 pounds per foot. So if I said, 500 pounds per foot is 0.5 kips per foot, not only does that change the barrier weight and the DC2, but it changes all the resulting moments and shears. If I hit undo, Control Z, notice how all the DC2s and whatnot have automatically been updated. So that's, a pretty valid reason to use Excel for a design project like this. And last, we have our future wearing surface, which we assume to be 25 pounds per square foot. I can delete this particular note. That's not valid anymore. Okay. That was during initial stages of building the sheet. So one of the nice things about doing this in Excel and doing this with a computational program in general, you can make notes. Make sure you document what you're doing and why you're doing it. Okay. So now that we have all of our input values, we can go ahead and compute moments and shears using the basic structural analysis shown below. I guess I should take this and copy and paste it over here and say I've assumed 15 pounds per square foot for the SIP forms. Again, make notes. Okay, so now we have dead load moments. Now we need live load moments. Now, as you know from class, live load moments are a little more involved. The first thing you have to do is compute a series of live load distribution factors. So this comes from a previous solution done in class looking at live load distribution factors. Now, because we're looking at an interior girder, you won't see any lever rule or special analysis done on this sheet because you really don't need to worry about it. All you need are the interior and exterior, or the interior moment and shear factors that are just empirical from the spec. So once you get your longitudinal stiffness parameter, which we've got that here, the N, the modular ratio times the quantity I plus A E G squared, which we've already discussed that in class. I'm not going to belabor that. The distribution factors are fairly plug and chug. So we've got our girder spacing, our span length, our kg, and our slab thickness, structural slab thickness. So we take 8 inches, and we can plug and chug out our single lane loaded distribution factor shown above, and then our that's for 1 lane loaded, and for 2 lane loaded or multiple lanes loaded, we have our factor as shown. And for shear, as we recall, the factors are a little simpler. There's single lane loaded and there's multi-lane loaded scenarios. Now for fatigue, we take the 1 lane loaded distribution factors, so the 0.68 and the 0.76, divide by 1.2. We divide out that multi-presence factor to get our fatigue moment distribution factors. We don't use these in this sheet, but we will later, and you will need those for the design project as we progress. So for now, I just left that in there. And same thing with deflections. We won't use that for the remainder of the sheet, but I went ahead and computed that out. So I have a nice little summary here for strength and service limit states. Here's the moment distribution factor, and here's the shear distribution factor for fatigue. Here's the moment and shear, and there's live load deflection. And again, everything is just referring to calcs that have already been made in the sheet. There's no reason to do stuff on the side. I mean, it's good to do these calculations once by hand to ensure that you understand what you're doing and that you get the appropriate answers. But once that's been taken care of, use Excel so that it will update all of your calculations automatically. Okay. Next comes the live load analysis. That's where we're actually combining the live loads to obtain live load moments and shears. Now you'll notice for these particular moments and shears that are shown, these were obtained using Leap Consys, which is the software we discussed in class, and these have been obtained for a 40-foot bridge. That's the bridge that I'm doing for my particular example. Some of you in your design project may be doing a 60-foot bridge or a 120-foot bridge or an 80-foot bridge and what have you. These moments and shears will change because as the bridge gets longer, the moments and shears increase. So what I've got listed are the truck, the lane, the tandem, and the fatigue truck. We don't have double truck and double tandem since this is simply supported. That's a negative bending investigation, so we don't have any negative bending. Furthermore, because we don't have any negative bending, all we have are case 1 and case 2. We don't have the case 3 and case 4 investigation that we did earlier. So we have case 1 and case 2, just 1.33 times the truck plus the lane, 1.33 times the tandem plus the lane, and just dragged all that out. And remember, we take the maximum of the positive values and the minimum of all the negative values. Now, we don't have any negative moments and negative moments on this bridge, but I thought go ahead and just include it just for format's sake, just so everything here is familiar. Now we take this governing case and we must distribute that to the girder. The distribution factor we got on the previous sheet was 0.916. Again, not typing it in, referring to the previous calculations to get distributed live load moments. These aren't factored because we haven't used strength 1 or service 2 or anything like that. Okay. Last thing, did the same story with the shears. Now, because with shears, we actually do get negative quantities because even on a simply supported bridge, you can have positive and negative shears. We do the same thing there. We get governing cases, 1.33 times the truck plus the lane. You can see that right here. And 1.33 times the tandem plus the lane, the 1.33 being our impact factor. Governing cases, use our distribution factor, and there you go. So now we have live load moments and shears, and this sheet, MV summary, is just summarizing everything in one nice, neat, concise little table. We've got our dead load moments and shears and our live load moments and shears. So all in all, I wanted to include this to just to have a nice little summary for myself. This sheet is not doing any calculations. Everything's just been lumped into one nice, tidy location. Okay, now once we have that, we can start doing some resistance calculations. Now, the first resistance calc we have to do is we have to look at plastic moment capacity and yield moment capacity. Now, I do want to take a little bit of time to discuss what's going on this sheet, because this takes a little bit of attention, and you really need to pay attention to what's going on, particularly in Appendix D. Now, what I've got here is the first thing I'm doing is I'm computing the plastic forces in the interior girder. So remember, when you're computing MP, you have to compute the plastic forces of each component of the cross-section, so the top flange, the web, the bottom flange, and the slab. So you'll notice here we've got the thickness and the width of each component. We're looking at an interior girder. And again, this is referring to everything that was back in the previous sheet. I also have the haunch down here because we are going to need that for distances later on. Now this is listing material strengths, either Fy or Fc prime, depending on what we're looking at. For the steel components, the plastic forces are just Fy times the area. So that's where this product is coming in, Fy times the area. It's just multiplying everything in the range. Same thing here and same thing here. For the slab, we don't use Fc prime times the area. It's 0.85 Fc prime times the area. So you'll notice there's a 0.85 there, and there's why. Again, this is just how I decided to arrange the sheet. You can arrange it in any fashion that you would like. Now, what I have here for this case determination is I wanted the sheet to do all the math for me, if you will. I didn't want to have to think. So what I had it do was run through each of the cases for plastic moment. And I've got here this little image down below. Remember, case 1 is where the plastic neutral axis is in the web. Case 2 is where it's in the top flange, and case 3 is where it's in the slab. And if you recall, determining whether which case we were dealing with is a function of the relationship between summing plastic forces. For instance, if we're looking at case 1, for case 1 to be valid, the plastic force in the tension flange and in the web has to be greater than or equal to the plastic force in the slab and the compression flange. So that isn't the case, so that's why it says no good. Now what I've gone ahead and done is, if that is the case, I went through Appendix D and said, well, if that is the case, what is the formula for Y bar, the plastic neutral axis? And this is the formula, taking all your rebar terms equal to 0, so I went ahead and just had it compute that. Same thing for case 2. Did a similar comparison. We find it is, again, not good. So if case 1 and case 2 are both not good, we don't need to do case 3. We know case 3 has got to be the case. It's got to be the one that governs. But again, for each one of these cases, I compute the Y bar, and I just go through the formulas that are listed in Appendix D. The last thing that I guess is worth mentioning is what's going on in this cell here. What this cell is doing is going through and step by step saying, what's the scenario? So I've got a nested if-then statement. So the way this is working is, first off, it asks, well, if this first cell, this F23, if that is good, then the first case is valid, and that's what my P&A is. If not, then we go further down the line. If the second cell is okay, then this negative, 0.586 would be the P&A. But since none of those meet the conditions, it's got to be that last value, E25, the 5.99, and that's the value that we go with. Again, using Excel to do all the grunt work for me so that I don't have to think later on when I decide, oh, I need to make that flange thickness 16 inches instead of 14 inches. Okay. Now, this table right here is probably the one that is going to give you the most headache. And it's probably because you didn't think that you needed to do it, but you kind of do. So let me explain what's going on. If you recall, in class, we dealt with a girder that was experiencing case 3. In other words, the P&A was in the slab. And don't get me wrong, that's exactly what we have for this particular example. But as soon as I start tweaking dimensions of the top flange, the web, and the bottom flange, and what have you, that may not be the case. In other words, it might not be a case 2 situation, it may be case 1. The problem with that is, as soon as I jump from case 3 to case 2, or case 2 to case 1, these distances change. Remember, these little D distances, these moment arms, are the distance from the centroid of each individual component to Y bar. So for instance, if I'm talking about D sub T is the distance from the center of that tension flange, somewhere about right there, to Y bar, which is somewhere about right there. Now, if Y bar is somewhere else, instead of it being in the slab, what if it's over here in case 1? What if it's in the web? Well, the formula that we use to get from the tension flange to Y bar is going to be different, okay? So for each one of these cases, you need to derive a distance. In other words, you need to derive a distance for case 1 from where Y bar is to, say, the center of the tension flange, where Y bar is to the center of the compression flange, etc. So you need to go through and derive all of those cases. Now, in class, we derived case 3. That was pretty simple. But case 2 and case 1, you need to go through and derive those to get those appropriate distances. So the idea is, imagine, let's say, for case 1. All right, so the Y bar is somewhere right here. Okay, well, how would you get from that line, let's say, to the center of the tension flange? Well, the total depth of the web, here, let me see if I can draw here on this sheet. The total depth of the web is D. So this distance is D minus Y bar, D minus the plastic neutral axis. But then I have to come down a little bit more, and that's half that flange thickness. Now, if you notice, if I go to case 1 and I look at DT, what do I have? I have D minus Y. Here, let me zoom in about like that. So here I'm looking at DT for case 1, and I've got D minus whatever Y bar is plus half the flange thickness. So you can see where that distance was derived for that case. Okay, let me go ahead and erase that. Give me one moment. Okay. You need to do that for each distance for each case. Now, if you'll notice, some of these have a not applicable, like this one, and this one. The reason why is if you look at case 1 and you pull the formula for MP, dW does not show up in that formula. Likewise for case 2, D sub C does not show up. So you don't need a distance where the formula doesn't use it. All right. Lastly, for each one of these cases, I say, well, if case 1 is true, what is MP? If case true is 2, what is MP? If case 3 is true, what is MP? And those are just plugging and chugging the formulas out of Appendix D, taking the rebar terms equal to 0. This last row here on the bottom is just a simple if-then statement to try and figure out which one of these values do we use. Do we use the case 1, the case 2, or the case 3? And since case 3 governed, we're using all the values from this bottom row. So this one, this one, this one, this one, and this one are all reported from case 3 because up here, that's what we found to be true. Okay. So the last thing that I really wanted to do is a little summary for my benefit. So the plastic moment itself, which is that value, and I took that and I divided it by 12. That's one thing you do want to be very cognizant of on these calculations is your units. All the formulas and all the distances in Appendix D will typically result in a plastic moment in inch kips. And since my moments from my analysis are in foot kips, let's convert everything back to be consistent. Excuse me. Now the depth of the web in compression, this is pretty basic. If you're dealing with case 1, the depth of the web in compression at MP, or this DCP, is going to be whatever Y bar is. In any other case, it's 0. So that's where that formula is coming from. Now this last one is in general how to get from the top, the very, very top of the section to the plastic neutral axis, regardless of if we're dealing with case 1, case 2, or case 3. And the reason why that's important is we'll need that to determine composite capacity here in a minute. Okay. Now, all those calculations are related to plastic moment. We now need to do yield moment, which yield moment's pretty straightforward. It's not very complicated. I start off by listing the unfactored DC1, DC2, and DW moments. I need my dead load moments. Okay, so I pulled those from the previous sheet where I had summarized all of my live load and dead load moments and shears. And those are all in foot kips. Multiplied those by 12 to get inch kips. Notice how I'm referring to this FY 50 KSI because that's what I'm after here. Okay, so here's how I've got this formatted, and again, you can format this however you would like. I've got non-composite moments, short-term composite moments, and long-term composite moments. Now, non-composite, let's start off with non-composite. So notice how we're looking at the strength 1 limit state, so you'll notice my load factors are going to be employed. Now, the only non-composite moment that I have is DC1, and since that's a DC load, the load factor for that is 1.25. So you'll notice 1.25 is employed right here. Now, in this table, I'm looking at the top flange. Over here, I'm looking at the bottom flange. So this section modulus comes from all the way back there when I did the section properties. I pull the non-composite top flange section modulus from that table, and it comes out to be about 614. So this component, M over S, has a stress of about 6.3 KSI. So that's the non-composite stress. Now I'm then going to jump down to the long term. Now the long term moments are DC2 and DW. So here's DC2, here's DW. Notice how I've got the appropriate load factors applied, 1.25 and 1.5, and again, same story. Now if all I were to do was add up those stresses, it would come out to be about, I don't know, maybe 6.8 KSI. If I made this term 0, I just deleted that. That'd be about 6.8 KSI. When I determine yield moment, what I'm trying to determine is first off, how much additional moment is required on the short-term section to induce yielding. So this little blue square right here, what I'm doing is I'm solving for how much additional moment is required to hit 50 KSI. And notice that's where I'm referring to right here. So solve that out in inch kips. That comes out to be 575,000 inch kips of moment. So I need that much additional moment to induce yielding. And I know that'll work because if I compute the resulting stress from that, it comes out to about 43.2, and I add all those up, that is in fact 50 KSI. So summing all of these particular moments up and dividing by 12 to convert to foot kips, the yield moment for the compression flange is 48,369.7 foot kips. Now that is an incredibly large value, but that's because we're looking just at the compression flange. It does take a lot of moment to yield the compression flange because it's so close to the slab and so close to the neutral axis. It really doesn't see that much stress in the composite state. Now the bottom flange, on the other hand, sees quite a bit of stress in the composite state because it's out there all alone. So the required moment to induce yielding in the bottom flange is much less. So remember, when you look at the spec, anytime is referring to yield moment, it's referring to the minimum of these two values, which came out to be about 5,094 foot kips for the yield moment. And that should come out somewhat less than the plastic moment, which it did, 6570. Okay. So we can start to do some limit state checks. The first thing that we'll do is service 2, which is a pretty straightforward check. Now we're not dealing with any hybrid girders, and we're not right now dealing with any lateral flange bending. We're not dealing with a bridge that's curved, and we're not looking at construction loads. We will look at construction loads later. For now, everything's straight and everything's homogeneous. So our limit on these stresses is going to be 47.5 KSI. And how do I get that? It's just 0.95 times the yield stress, if you recall the limit that we discussed in 610.4. Now, that limit has to be compared against the service 2 stresses, which are taking each of these individual moment components, dividing them by their respective section moduli, and applying the appropriate load combos, which, if you recall, all of the load combos for service 2, all of the load factors are 1 except for live load. We up that by 1.3. So you'll notice all of the live load factors are 1.3, all of the dead load factors are 1. So here's the moments. DC1's on non-composite, DC2 and DW are on long-term composite, and live load is on short-term. Now you'll notice the live load that I'm querying, I wanted to spell this out. It's the unfactored live load moment from the positive column, because we're dealing with simply supported structures. We only care about the positive bending. And this is after the live load distribution factors have been applied. So you'll notice I'm pulling a value of 665.3. If you go all the way back to the MV summary, I'm looking at moments. This is after the distribution factors have been applied, 665.3. So that's the value that I'm pulling. So here's the moments converted into inch kips. Here's the section modulus. M over S gives me a stress. Sum that up. So it's about 6.1 KSI compared to a limit of 47.5, and we're good. We're in fact really good. The performance ratio for this is coming out to be like 1.3. Okay, but again, if you recall, we're taking the girder from our design example in class and applying it to a 40-foot bridge. So yeah, it's going to come out way over design. But this was just to generate some familiar numbers and demonstrate the effectiveness of these calcs. Remember, we can use our rules of thumb that we discussed in class to generally size a girder, and then we can tweak that using Excel. Now, the bottom flange doesn't perform as well, but it's still performing way above and beyond the call of duty because, again, the girder is so significantly over-designed. And we see our performance ratios. Now, these performance ratios are highlighted in yellow because they are a very nice, concise, but descriptive definition of the performance of the girder. If I could, I would make all the performance ratios for this bridge to be 0.999999. In other words, just as close to 1 as it could possibly be without going over 1. Now, it is impossible to achieve 1 or close to 1 on all your performance ratios, but there will typically be some that govern your design, and they will, in fact, either be equal to 1 or very close. The long and short of it is, if you can get those performance ratios to be in the 0.9 to 0.95 range, you're doing pretty good. So all in all, this bridge meets the service 2 limit state very well, as would be expected. All right. Now for strength 1, I've got a sheet calculating the composite capacity and the non-composite capacity. Now one of the things I've pointed out on my sheet is I'm pretty much automatically assuming in these calculations that the section is compact, which by and large is a pretty reasonable assumption, especially if you're the one tailoring the girder. You can most likely tailor the girder to meet these requirements. And plus, for my particular example, I'm looking at a simply supported 40-foot long bridge. It's not like a multi-span hundreds of foot plate girder bridge where, you know, the girder really does get pretty non-compact and pretty slender. In a 40-foot bridge, the girder should be fairly compact by osmosis anyways. But what I wanted to do in the sheet was put a little note that, you know, I'm doing the check to ensure whether or not this section is compact. If it's not compact, I'm going to have to do additional calculations to determine the capacity. Essentially, it's limited to the yield moment, but even more so, 610.7 stipulates that if you're dealing with a non-compact section, you're not even dealing with moments anymore, you're dealing with stresses. So we'd have to compute resulting stresses from our MV summary that we did earlier, and there'd be a little bit more going on. So I just wanted to have that pointed out. Now, specifically into the calculations, for a section to be compact, we have to meet 3 criteria, and we're talking about composite girders right now. Non-composite girders, it's a whole other can of worms, and we'll talk about that later on. But for composite girders to be considered compact, we have 3 criteria we must meet. The yield stress must be less than or equal to 70 KSI, so here's the yield stress, there's the goal, so we're good. The web slenderness must be less than or equal to 150. Here's the web slenderness that we computed actually way back on the section property sheet. Here's the goal, we're good. And the web compactness check. Now this web compactness check, I've got a little formula here showing you what exactly it is I'm computing. The limit, or the goal, I guess I should say, is 3.76 square root of E over Fy. So that's this term right here, 3.76 square root of E over Fy, and I just referred to that value right there for Fy. What I'm comparing that against is the web slenderness, or the web slenderness of the compression portion of the web at MP. So 2 d sub Cp over Tw. Now, I computed d sub Cp on the previous couple sheets. That's this term right here, the depth of the web in compression at the plastic moment. And since the plastic neutral axis was in the slab, all the web is in tension at MP, and that came out to be 0. So this term 0 against the goal, we're good. And that usually will be the case. Now if that is the case, we've got our compact section flexural capacity, which is computed with the following bilinear model that you see right here. It's either MP or a linear fit off of MP, and it's pretty straightforward. So I've got d sub P, d sub T, d sub P, which is what I computed here, from the top of the section to the P and A. D sub T is just the total depth from the way bottom to the way top of the section. Now the dP over dt ratio came out to be 0.11, so that means we're not using this upper expression of MP, we're using this linear fit. So here's the linear, here's plastic moment, and there's the linear fit. If that value is less than or equal to 0.1, we're going with MP, otherwise we're doing this. And I went ahead and multiplied the whole thing by 1 just to show you that I am in fact incorporating the resistance factor, the LRFD resistance factor. But for bending and shear for steel, it is in fact 1. So you don't necessarily have to throw that in there, but I just wanted to have it in there so that we're considering it. Excuse me. Now, we compare that against the actual moments that are being applied. So we've got DC1, DC2, DW, and the live load. factor those out, so 1.25 times DC plus 1.5 times DW plus 1.75 times the live load gets this. Here's the load, here's the resistance, we're good. Dividing those two, we get a performance ratio of 0.248. Now, again, this is way over-designed, way over-designed. Typically, what you would want is this girder to be probably much more shallow, and the flanges would be a lot less beefier. But in the end, I think we can, once we have the sheet set up, we can tweak the dimensions as necessary. Okay, so there's strength 1 for the composite stage. For non-composite, there's a little more going on. So what I've done is I've split this up into 2 sheets, and I've got some annotations on the side that I think will make this a little easier. Now, I went ahead and just decided, you know what, let's go ahead and determine that this girder is in fact compact. If it's not compact, we have to use 610-8, but and we would have to do some additional calculations to ensure that. But I'm going to do my very best to ensure that the girder I design is in fact compact because it's more economical anyways. So we have 4 checks that we need to meet. Our skew's got to be less than or equal to 20 degrees, which we're dealing with a straight or a right bridge, so skew is 0. The yield stress has to be less than or equal to 70 KSI. And then we've got 2 checks related to web compactness and the T-sections. It's a little different than 610-2, but on the same vein. Instead of, actually I forgot a little arrow here. Let me see if I can copy and paste this. Put that about right there. Okay. Instead of showing you every single formula, the idea was these little annotations on the side would show you what's being computed. For instance, this 2dc over tw, well, dc is referring to the depth of the web in compression, but keep in mind we're talking about the depth of the web in compression for the non-composite section. So it's literally just that upper portion of the web in compression for the non-composite shape. And again, we've computed all of these values by hand, so this should be some pretty basic stuff. So here's the first limit, we find it's good. Second limit, we find it's good as well. Maybe I should increase the accuracy of that. Okay. Now, excuse me. Now to do Appendix A calculations, unfortunately, we need a lot of background data. So there's a series of sections down here below that is reporting a lot of the pedigree terms that we're going to need in order to attack these calculations. And we did a lot of these calculations by hand in class, so I won't belabor them too much. But you'll notice we need elastic section properties, particularly the yield moment and the depth of the web and compression. Again, do not confuse these with the stuff that we did before. This is for the non-composite section, so we just pull those right from the section properties. For the composite shape, that's where we have to go through and do the additional calculations like we did on this sheet to determine the additional required moment and what have you. We're dealing with non-composite properties here, so just, you know, pulling straight from the very first sheet that we did. Now, for the plastic moment, we do need the plastic moment of the non-composite section, but I was a little lazy with this calculation. Specifically, I spent a lot of time getting the composite section right. I propose to you that a non-composite girder is simply a composite girder with no slab. So all I did is took all of the calculations that I did for the slab all the way back here, specifically, you know, all this stuff with the plastic forces and the P&A and all that. All I did is I said, all right, let's just redo those calculations with no slab. So I set all the slab terms equal to 0, and all those derived distances that I had derived were valid because I derived them symbolically. You know, I was looking at, you know, d minus y plus the flange thickness over 2. I didn't use numbers. Again, letting Excel do all of the work for me. So going through and doing all of this, you can see I even retained some of the labels like this F5 or FC prime. Really, it's just Fy because there's no slab. So go through and do all of that, and you find that the plastic moment ends up being about 3326. Again, this is a value that we got in class. And the depth of the web in compression ended up being just Y bar for case 1, this 31.857. All right. The last thing that we need are some properties for Appendix A. Now, I'm not going to go through and highlight each individual cell, but that's sort of what this whole series of formulas on the right are. For instance, if you look at the formula for E48, the radius of gyration, okay? Now you look here, there's D33 minus square root of da-da-da-da. In the end, that's just this, okay? So everything that you see in that formula is referenced right here in this image. So this is one of those things where I imagine you all are going to be pausing and playing and pausing and playing. That was really sort of the whole point behind the development of this. Now, here's our radius of gyration. We've got our torsional constant J. We have the flange moment arm. I didn't put the formula here, but it's just it's the sum of half the flange thicknesses and the web depth. It's pretty basic. The reduced yield stress, since everything's the same yield stress, you notice I'm referring to J8 quite a bit. More often than not, you're going to find that this comes out to be 0.7 times the yield stress, or 35 KSI. Now, I've called this LTB anchor point 1 and 2, so just LP and LR. The only point I will make, and I think it's easier to see on LP, if you notice there is a slight difference between what's shown in this little box and what's in the formula, and that's dividing by 12. Because when you just plug and chug, you're going to get an LP in inches. But later on, as you're going to see, we're going to need an LP in feet. So you're going to need to be very cognizant of that. It's in there. It's a little hidden. I think you'll find it right here. But it's in the LR formula as well. This formula is a little more involved, but I did want to divide the whole thing by 12 to ensure that the units came out right. I think I put the 12 right here next to this FYR. So it's 1.5 times RT times E divided by 12 times FYR. Okay. Last thing I computed on this sheet were some slenderness properties for the flanges and the webs. So for the webs, I've got 2DC over TW. I've got the second anchor point. I know for webs it seems a little strange to compute the second one first and then the first one, but you use this quantity for the first anchor point that you'll see here in a second. Now, the second anchor point is just 5.7 times the square root of E over Fy. For the first one, it's a little involved. You first have to compute what I call a plastic anchor, which is this quantity that you see right here. Once you get this, you can compute the first anchor, which is right there. Okay. For the compression flange, maybe what I ought to do is box that, so I'm sort of separating the web and the flange. For the compression flange, you need the slenderness, which is BF over 2TF. You need a plate buckling coefficient, which I'll show you what I did here. The formula is 4 divided by the square root of, let me sort of pull that up here, of the D over T for the web, so 4 divided by square root of D over T. But it's got to be between 0.35 and 0.76. So I said, whatever I calculate, let's take the maximum of that and 0.35, and then for that quantity, take the minimum of that and 0.76. So that way I would ensure that whatever quantity I calculated, it would be between 0.35 and 0.76. There's probably a couple other ways that you could do that mathematically, but I personally think that's the easiest. You could probably do some if-then statements or something like that, but I think that gets a little too convoluted. The last is the flange slenderness angles, lambda P and lambda R, and you can see those are pretty plug and chug. I have all of that on a sheet by itself, and I refer to it on this part 2, where I'm computing the capacity. Now let me zoom out real quick, and I'll show you what I've got going on. So this first set of calculations is for the web plastification factors, the RPC and RPT. and the last one's for the capacity. I've got up here, I've got flange local buckling. Here I've got lateral torsional buckling, and then I've got tension flange yielding, which is a simple check, or a simple calc. There's really not much to it. So let's start off with web plastification. First off, here's the formulas that you see right here, and I know it's fairly involved, so I wanted to take it step at a time. So to start off, I've got this box here on the left, and I have computed, or haven't computed anything here. All I've done really is referred back to a lot of the stuff that I calculated before. For instance, MP, the MYC for the compression flange, the MYC for the tension flange. I'm just pulling all those values that I computed earlier. I think some of these formulas get a little convoluted, so I wanted to have them all in one nice place right here so I could type in my formulas correctly. So you notice that these are all sort of listed out, all the ones that I'm going to need. Now, I'm computing two web classification factors, an RPC and an RPT. So here's all the RPC values, here's all the RPT. Now for RPC, we'll take RPC just to be consistent, or just to be thorough. We have two cases. Case 1 is MP over MY. So you notice that's MP over MY. For case 2, it's a little more involved, but all in all, I'm pulling all of the calculation, or all the values that you see there on the left. So the minimum of 1 minus the quantity, 1 minus the hybrid girder factor, which I'm taking to be 1 for this entire sheet, times my over mp, times the following linear interpolation. Web slenderness minus anchor 1 over anchor 2 minus anchor 1. And that's the minimum of that times the former ratio, or the former ratio. So I know that seemed pretty convoluted, at least in terms of explanation. And again, you can pause the video to your heart's content and go back through that. That's sort of the whole point of going through this on YouTube. So I've got case 1 and case 2, and then I just have a pretty simple if-then statement that says that if 2 dCp over Tw is less than or equal to the plastic anchor, then we're dealing with case 1, otherwise we're dealing with case 2. And once you get the formulas for RPC down, RPT, it's very similar. It's just some very minor tweaks to the formula. You're dealing with MYTs instead of MYCs, and there you go. Okay, so there's your RPCs and RPTs. Let's deal with the compression flange capacity. Again, very similar layout. Over here on the left, I'm pulling all the values that I need. The flange slenderness, anchor 1 and anchor 2, so that's lambda PF and lambda RF. Web plastification factor, RPC, which I computed up here, came out to be 1.076. The yield moment, the reduced stress, and the section modulus. Everything that you need in this formula is listed over there on the left. And then I compute case 1, that first row, which is just RPC times the yield moment, and then case 2, this linear interpolation. Last, an if-then statement. I guess if I wanted to be consistent with previous formulas, I'd do 1 times that, just to be cognizant that I am, in fact, including feet. So for this girder, case 2 ended up governing, and my flange local buckling capacity was 2731. Now, that's flange local buckling. Lateral torsional buckling, it's a little more involved, but it's pretty, in the end, it follows a very similar pattern. Over here on the left, it's again, I'm pulling all the values that I need. Now there's a couple new values. I've got the unbraced length, which is the distance between cross frames. Since this is such a short bridge, it's 40 foot long, I'm going to say I only need 3 cross frames, 1 at each end and 1 at midspan. So that means the unbraced length for this girder, regardless of what side I'm looking at, is 20 feet. Okay, so I've got 20 feet, and I've got the LTB anchor points LP and LR, so we can tell just by looking at this that we're in zone 2. So we're in this inelastic region, and ultimately we're going to take this longer expression here. And if you look here, that's what happens. For case 2, we got 2166, and that's the actual quantity. Okay. Now, a couple other things we need. We need a moment gradient modifier, which I'm taking that to be 1 but we did discuss that in a previous class, how to compute that. So I wanted to, just have that out so that you all would have that value there. A couple of the other quantities, things like the radius of gyration for LTB, the torsional constant, the moment arm, all the section properties that we used above, and then going through the motion. So case 1, just RPC times the yield moment. Case 2, this linear fit off of that. And you can see the formulas there, and I'm sure some of you are going to hit pause, and that's fine. I don't have a problem with that. I just want to make sure you're understanding what you're doing and why you're doing it. And then for case 3, the formula is a little more involved because we have to include this FCR. So this FCR, you can see that down here. And again, it's pretty straightforward. The only thing I would point out is this slenderness term right here. So LB over RT. LB is in feet, RT is in inches. So if you'll notice, right here I've got LB times 12 over RT squared. Make sure you're converting. Simple if-then statement. Last, for tension flange capacity, it's just RPC times the yield moment. That's it. So if you look, I'll scroll up a little bit. Let's see. RPT times the yield moment. And there you go. And that's it. So all in all, that came out to be about 3,326 foot kips. Now again, while we did not use the tension flange moment capacities directly, we do in fact use those later on when we do constructability checks. So that's going to be very important for later, and we need those quantities there. So I know this spreadsheet seems like a lot of work, but all in all, it's far less work than if you were to iterate and have to do all these calculations by hand again. Imagine if you were designing a bridge and suddenly the girder came out no good and you had to make the wed depth different and then you had to do all of these calculations again, all by hand. It would be maddening to have to iterate that by hand. So you all need to be working in class to develop a spreadsheet like this. You can do it however you like. It just needs to be followable and neatly organized, not just for my sake, but for your sake. And to anybody just generally watching this video, I hope that this serves as at least a brief guide on how to go about setting up a spreadsheet and doing a lot of these, what may seem like complex bridge engineering calcs, and some of them I can imagine seem that way, but all in all, what I have found about bridge engineering is that it's not hard, it's just long. But once you get something like this set up, it really doesn't become long ever again. You're the one who's set this up, and all you have to do is iterate, and it'll do all of the calculations for you. That's all we have. We'll see you all when you get back from break.